great again. So I'm going to basically talk about how I made a VNA. So a quick outline. I want to explain, what is a VNA or why do I even want to do this? I mean, how many here don't know what a VNA is? Good, great. So if nothing else, you should learn something. So then how do we go from an idea to basically having a product? So I didn't know anything about microcontrollers. I never did PCB layout. I had soldered 0201s and stuff like that, but I never put like BGA components down, and my development process. So, sound good? Okay, so my professional background, too much knowledge on antennas. Okay, so antenna PhD, all my career experience is in antennas, so when he handed me this, it's almost offensive. Like if this is what antenna engineers did, I had wasted my life. All right, put that away. Okay, so I'm only going to talk about antennas for like 15 seconds. Basically, I want to say, when you're designing antennas, most of the time, you don't need anyone with anywhere near this much experience. If you're just doing like a Bluetooth thing, you have no constraints, you just design it yourself. You're not going to have a problem. Your range is going to be fine. You don't need all this stuff. You don't have to pay me. You only need this much experience if you're doing like something with a lot of metal or really constrained, or you have a 20 bands LTE stuff, or a GPS. Or if all your RF guys tell you that the antenna is broken, then you probably need an antenna guy just to show you what else is broken. So actually, the reason I'm telling you this, it's not because I'm trying to like give you antenna knowledge. It's actually going to be a philosophy going forward. Is when I don't know how to do something, I'm not going to ask the expert. I don't care. I'm just going to do it and figure out how far I get or what obstacles I can do. So, like again, going into this, I know nothing about embedded, but we're going to make a product. Okay, so what's a VNA? It's a critical piece of RF equipment. So that's measuring things like 100 megahertz, 2.4 gigahertz, high frequency stuff. We want to know the fundamental thing we're going to measure, especially with antennas, is S11. That's basically, we're just measuring the impedance of a device at high frequency. So with just a one-port VNA, we can design and tune antennas, RF impedance matching. So if you want to deliver energy from your radio to your antenna or whatever it is, the impedances need to be matched. Measure your transmission line impedance, characterize materials, whatever. And if you have N-port, characterize like your LNA response or isolation between antennas. Okay, so what's the problem? These things are too expensive. So if you want something that's full-featured, that has like port extensions so you can see exactly the phase plane you want to see, it's extremely expensive, and I've always not understood that. And with that, they'll sell you cal kits that cost $12,000 for just very accurate cal standards so you can calibrate your device. And if you want, like an automatic cal kit, it's like $14,000. It's ridiculous. And as I started doing this project, I actually started to realize how deep the rabbit hole goes, where if you actually look at the math and calibration, you don't need accurate cal standards at all. You only need 3 independent loads. So if you look at the math, the math is simpler if you had like open load short, but if you don't have that, you can use arbitrary loads. It's just a system of 3x3 equations that anyone can solve. So, oh yeah, if you want to take pictures of this, feel free. And I also have my email at the end because I'd love to hear feedback or if you have more questions on stuff. Okay. And what really upsets me is like, so at Apple, everyone has when you're an antenna designer at Apple, everyone has a VNA on their desk. And it's critical. And every year they come by and they got to take the VNA away for 3 days to calibrate it. Why? So all of you have 5 radios in your pocket. All of them have frequency synthesizers. All of them stay at 2.4 gigahertz for several years. It doesn't make sense. This doesn't add up. Why do they need to take my VNA? We have to have this really expensive, calibration, service plan, whatever. It doesn't make sense. Once I was talking to a vendor and they told me I need these like $1,000 phase-stable cable. And a phase-stable cable is such that you bend it and the phase doesn't move. But the whole point of a VNA is you can see the phase on there. So you know if it's there. And the guy was like incredulous that I didn't want it or didn't need it. And again, the calibration kit. That is just ridiculous. So one of the things I did on my thing that ended up being innovative is I have integrated automatic calibration, and it's just as good as, you know, the $14,000 version. Okay, so given this, I'm going to explain a little bit more about how VNA works. But this is why I want to do it. So let's get on. Okay, so real quick, how does this work? We just need to measure voltage over current. Very simple, right? And so we do this at every frequency we're interested in. So we can pump out like 900 megahertz and measure the frequency. So we're actually measuring reflection coefficient, which is equivalent to measuring the impedance. So for instance, if you have a 50 ohm load on a 50 ohm port, there's nothing reflected. Your reflection coefficient is 0. If it's open, all the power is reflected. So to do this, what we have to do is have a source. So that's, you know, your PLL VCO oscillator. And we apply it to a load, and we need to measure what's reflected relative to what's incident. So far, there's nothing hard here, right? So how do we get the incident and reflected voltage? So we have this thing called a bidirectional coupler. So what it does is it puts the energy in one port, comes out the other. This is where your antenna would be, or whatever you're measuring is reflected. And this port picks off some of the energy that's going this way, and this port picks off some of the energy that's going that way. So if we have a device like this, using these two measurements, we can get what we're looking for. So the parameters we care about, I'll define S parameters in a second, but basically the insertion loss, how much energy do you lose going across this? How much energy couples down here? How much energy couples down this way for reflected? And then the energy you don't want is forward energy coming down here and reflected energy coming down here. Okay, and so as a block diagram, we inject energy. We have a bidirectional coupler, and we have two ports, the incident and the reflected. And all we have to do is measure the relative power and phase, and we have the complex value for the reflection coefficient. Again, in your pocket, you have 5 radios, and 1 billion times a second, wireless communication happens by sending magnitude and phase. All the bits are encoded that way. So you all have 5 radios. You've done this literally 9 billion times today. So it's unclear why this is hard. Okay, 2-port VNAs. So that is, you put in energy in one port, and you measure how much goes to the other side. So you do that if you're looking at you know, the insertion loss or something, isolation between 2 antennas, the gain of your LNA, that sort of thing. So they call it S21. That's transmission coefficient, which just means if I inject energy out of port 1, how much do I receive at port 2? So in general, S parameters is always like S11 or S42. That's just energy from this port to that port, with like S11 being reflected power that tells you the impedance of each port. Oh, and it's actually easier to do the second port because you don't need the bidirectional couplers on this side. You just measure the power. Is there an easier way with SDRs? Kind of, yes. I did a mock-up. It works. You try to like package this up, though, it sucks. You end up needing to install GNU radio. I know some of you guys probably can do that. That's 8 hours of your life you're never going to get back. I hate it. I hate it. This is, you cannot do this. You're going to be on the phone with people, oh, I have Linux 15 and running this. It's your entire life. So this, no, you cannot do it this way. Okay, finally, we have to choose a frequency range. So in consumer electronics, we care about mainly this spectrum, like up to about 3 gig. You care about 5 gig, but for this product, I could do it, but I have to do another build. So basically, GPS, 1575. You got a bunch of LTE on either side. Wi-Fi, Bluetooth is over here. European LTE is over there. Some TV down there. So basically, GPS, Wi-Fi, Bluetooth, a lot of stuff you care about in cellular, you can all design if you have this frequency range. This is why I care about those frequencies. Schedules. I love schedules because You sit back and you say, okay, I don't know how to do this, but I'm going to make a list of what needs done, and I'm going to knock it out. And if you're stupid and you have a schedule, you'll at least learn that you're an idiot, right? You'll be like, oh, couldn't do what I said I was going to do. Maybe I'm not as smart as I did. But if you're able to do it, then you're like, okay, I made a schedule. I didn't know how to do something, and it's good. So I love schedule. There's exclamation point there. All right, so what I did is I made the schedule in, I don't know, it's like May. And so like, I don't even know which microcontroller I'm gonna use. I have to do that, so June. I have to blink an LED, step one. I have to control display. I'm gonna have to make a schematic, figure out PCB layout. I'm gonna have to be able to control this, the frequency synthesizer. All stuff I've never done before. You know, evaluate my bidirectional coupler. So here I have, you know, early stage stuff. I have a dev board, Proto 2, and then working my way to more mature stuff. You can always tell like when a Kickstarter is going to fail because they have a crap prototype and then they're going to production 2 months later. If you don't have like the time in there to get this right, you're already going to fail. And as we see as we go through this, I have a bunch of subtasks that pops up. It's like, okay, that didn't work. I need to reschedule. How do you choose an MCU? That's hard. This stuff was black box to me. I've never done it. I mean, I don't know how to blink an LED. I'm scared. I'm like, okay, I'm going to buy this thing out DigiKey. Step 3 is profit. What do I do between there? Like, I have no idea. I don't know anybody that does microcontrollers. So, you know, if you're like at a company like Apple, you have a whole team that knows the roadmap and the capabilities. They look at power draw, the speed, all the capabilities. You're in front of their roadmap, so you know what's coming. You know, and you don't have to worry about documentation because you have somebody that's going to come to your you know, site anytime you want and answer your questions. Well, I'm going to have none of that. So what do I care about? I only care about 2 things. Can I get the thing, and is it well documented? So what I was doing is I was looking at Hackaday. There was a product that this guy I was kind of following. He used STM32F4, and I had one friend who could blink an LED. And he actually knew just more than I did. He was using that. That was it. Done. We have a microcontroller. And as I had mentioned, like, I was scared when I was getting the microcontroller because it was like, okay, I'm going to order this thing, and like, how do you know what to do to make that start doing what you want to do? It doesn't come with Linux. I can't terminal into it, right? So, and how do I figure this out? I found this tutorial, and it was some guy who's basically selling his board. It's just the chip and the bare minimum, like what you need to do to blink an LED. And I was like, this is cool. So I started following this tutorial, and I was like, you know what, I really like this. I didn't actually understand much of it, but this is how I selected the IDE, so kind of cool. I really like this. There's no clock in here. I have written code, scientific code, C, MATLAB, Python. When I saw this, I was just like, wow. I didn't have a clue what that meant. Like Marianne, when you're looking at this, same way, like I was seeing it. Unbelievable. Anyway, but you do this and you fight through it. You do it once or twice, and all of a sudden, like, you know, the third time you do it, it's just like antennas. It's all black magic till you've done it 10 times. You know, I developed this model in my head. You know, the microcontroller is just this big set of registers. You set the registers, it'll do what you want. And it's very well documented. It's the same thing every time, and it turns out it is not hard at all. So I blinked an LED, and when it happened, it was huge because it was like, if I could blink one LED, I can blink 64 bits and do all these drivers and all this. It was like, I immediately know like the next 30 steps are done. So that was huge for me. And also in that tutorial, they talked about going through the reference doc and like how you figure this stuff out. And it was just really cool. It's super logical. It sucks at the beginning, but once you're through it, it's actually really simple. I apologize for that meme. Yeah, so controlled the microcontroller. So then I start doing the other stuff. Like I need to make an analog digital converter. Check your inputs, do interrupts. Again, the hardest part is blinking that first LED. So we need a display. My requirement is this thing is documented. And also a lot of people use this one. But you basically go to the data sheet, and it has this. And I still don't even understand. Like, what does this line mean? Does anybody know? TB? I don't. And like here, it's like there's a 0 here, and they don't leave it down. It's like they're letting you pick, but they write 0. It's like, leave it low. Anyway, so this is like stuff I'm trying to figure out. But, and then the STM, it's like, we have 2 SPI ports or buses or whatever. It's like, I don't care. Well, I don't need to do that because I'll just bit bang it. So I literally like clock high, clock low, data high, data low, whatever. I just write this. And it turns out you actually don't want to do that, but I didn't know why. It works, but it's actually just slow. So again, I don't like asking people. I don't like installing anybody's libraries. I hate it. Like, I'd rather take 2 hours to do something than spend a half hour installing somebody's library. I have no idea what's going on. So I didn't know why to use the onboard SPI bus, so I wrote the bit bang. I learned it's much slower. Now I know that. So yeah, so I was using a discovery board and controlled that guy. So from here, basically now we want to go about building the actual product. So simple block diagram, just what I showed you before. Frequency synthesizer VCO. That puts out the energy at whatever frequency we want. We have bidirectional couplers that are going to come down here to, again, a magnitude phase detector, which just tells us the relative magnitude of what's coming in the phase. Again, done 1 billion times a second in your phone. And SMA edge mount connector. Really simple. SMA is just a common antenna connector. Yeah. So also now, I've never done PCB layout. So Cadence is very expensive. It's Allegro. They use it in your big consumer electronics firms. Altium's used a bit. I knew a couple people that used Eagle, so I ended up using that. What I don't like is they did just change the pricing structure. So had I been starting this project now, I might use KiCad. I know there's a guy with a hat on that doesn't like that. Yeah. Okay, as far as then going from your block diagram to your schematic, you just get the reference diagram. You're not smarter than the people who make the reference document, so just get that and you copy it, right? So no tricks there. You have to make the parts that's not hard. Here's my first board. So I'm like, whatever, I'm gonna make 2-layer board. I have it. I'm not good at it. Anyway, so made this guy. Kind of cool. So again, the goals of the dev board was demonstrate controlling the VCO and maybe see if I can measure some of the other stuff with the bidirectional couplers. We got to learn how to put these parts on there. So I'm going to talk through that real quick. You want a lot of this equipment. So like a hot plate helps keep your board nice and uniformly warm. Heat gun for applying heat over the part. Solder iron is super useful. This cleans copper. You want leaded solder. Use the good stuff. We know it's toxic, but it's good for it. Yeah, people don't use lead because they're stupid, right? Like leaded paint, it looks nicer. Leaded solder, it's easier. Flux. Flux helps distribute the heat on your stuff. And alcohol you can clean. So real quick, the hardest part I had to put on is this guy. It's basically a switch. So the pads are like 180 by 200 microns. So how do I do that? So the steps are, I put flux on the chip, I put flux on the board, and then I just take the solder iron and I dab it all on there. So I get a little bit of solder on each of the pads, a little bit of solder here. From experience and doing this a bunch of times, you learn that like a lot more solder ends up on the center pad than the other pads. So then I take the copper wick and remove the solder from the center. And then you clean it again with the alcohol, make that board nice and clean. Put another layer of flux on there. And then here, you sit there under the microscope and you spend 5-10 minutes making sure this guy is exactly lined up to within 10 microns. And as long as it's going to take you. It's not easy, so you have to nudge it a little bit, nudge it back. Then you apply the heat. Apply the heat. Check the parts, as particular RF components will break. So, more heat, it'll get on there quicker, but you will break the part. So do a quick check on that. That'll waste a lot of your time. Yeah, so you turn the heat plate on, you hold the gun above it after it's sitting there very lowly. I use no air and just heat and slowly move it forward. This part here, that process I just described, took me about 75 minutes. So I put it on there, it didn't work. What are you gonna do? You take it off and you do it again. So it's conceptually simple, but you have to have a lot of tenacity to get it done. Not the board. If I use too much heat, I'll damage the chip. Never damage the board. Okay, so we're flying here, right? We got our first 3 bullet items done, and now we have to bring up the synthesizer and start looking at how things are going there. So the synthesizer, it's actually a really cool circuit. We're just buying an off-the-shelf chip, but what it does, you have a reference crystal. It divides it down to some frequency reference. The output is here. It divides the output by some integer or real number that you control. It compares the frequency, then the phase, and then determines lock, and goes through like this. So like in your phone, there's specific frequency channels for Wi-Fi. It might be separated by 10 megahertz or something. Well, then the delta that's coming in here is 10 megahertz, and the n just multiplies it up for each specific frequency you're using. So really cool stuff. In our case, we're using a fractional n PLL that allows us to basically set arbitrary frequencies. So we don't have to use an integer value of n. We can use 14.258. The SPI interface, so for the PLL, I couldn't find any documentation online, so getting this done is a matter of going through the whole document. That's why one of the biggest things I care about is having good documentation, because I'm not going to be able to call the vendor. I don't have any friends doing this. I don't know anybody doing this stuff. I'm just going to have to fight through it. And it's all about tenacity. A lot of this stuff, it's not anything you have to be smart to get done. It's a matter of failing and, all right, again. Because again, the first time you do something, it's very difficult. The third time, it's stupid. So I have nothing else to say about that. Okay, so I'm able to cycle through my, so now I have drivers for my display and I can control the VCO, and that's awesome. So start doing some actual RF testing, and my bidirectional couplers are totally useless. I cannot tell the difference between total reflection and complete match circuit, which means the board does nothing. So the bidirectional couplers have a spec sheet, and the problem is it's all measured with exactly 50 ohms. And I kind of half-assed this layout, and I knew okay, I have to do really focus on the RF stuff now, because one of the things actually being an antenna engineer, we don't care if there's no 50 ohms in the antenna land. You just can make anything work. So I was okay, if it's short, I'll just cal it out. It'll be fine. But it wasn't. So I have to now make a subtask, which is fix bidirectional couplers. If I can't make my bidirectional couplers work, there's no reason doing any more work. So I had to make a auxiliary board. So this was an unplanned diversion. And here I basically got several different bidirectional couplers. I put some on the lines with printed traces. Really put a lot more work into the layout, making sure the traces are good. And here's the data. So I was able to see how what I can produce compares to the spec sheet. So again, what we really care about is how much different these two curves are. The black is kind of how much energy we're picking off in the forward direction relative to the energy that comes out at the back that comes into the same port. We don't like that. So over here, this bidirectional coupler is useless here. So even though the spec sheet might say it works, or your simulation or whatever says it works, it doesn't matter if you can't build it. So here I'm able to say, okay, now I know exactly which couplers are going to do what I want them to do. So I had to do a diversion here. Proto 1, my first board. So going to 4 layers, I know I need to keep the RF section very pristine. Same exact chip on the discovery board. And here I wired out every single pin because I'm scared that they're going to be like, oh, you didn't have boot 7 wired out, and that has to be set to 25 kilo ohms, right? Something stupid. So I literally wired out every single pin, and because I'm just like, I need to be able to flash this. And I was really worried that I wouldn't be able to. So wired out every single pin. Here's the connector for the display, and here's your RF section. Yeah, and started, my first attempts at user interface and stuff. I'll show that. Yeah.
2 slides ago, you had the graphs and radio things. Now, what tool did you use to do that?
I do have access to a real VNA. So. But I'm putting them out of business. Yeah, I couldn't use the product I'm developing to get this causality. Okay, so actually this one went really well. Put a lot more work into how this was coming together. How much time do I have? Okay. How much time? A lot more work into this, and then, okay, clearly I can see the difference between open, short, load. I'm happy, things are getting much better. Yeah, I went to 2-side SMT, I don't care. Costs a little bit more. Definitely paying up for more boards, tighter spacing, that sort of thing. Okay, so what are we going to do about UI UX? This doesn't run Android, right? I don't know how to install Android. It doesn't run iOS. So I started thinking about like how's the user going to interact with this thing? I've always hated touchscreens, so it's good because I don't want to write another driver anyway, so that's good. As far as displays go, I only know how to make rectangles, but we'll see how much you can do with that. So here's like actual brainstorming thing I have for my notes where I started drawing like what I think this is going to look like, and I started making priority 0 features and what's priority 1. Here's me figuring out exactly what I'm trying to do, and here's like prototyping. Okay, I need to be able to sweep through this stuff, and I'll have the frequency like this. This also isn't too hard. I didn't want to read in a library. Like there's like you read in a library to put characters on a screen. No, and I don't want to download your code and follow your instructions. Like you cannot let the computer scientists win. Like just do it yourself. So like if I have a function called like print s, and it just goes to the location of like pop, 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 all this. So every time I needed a character, like here I'm making the word start frequency. I would write a function, place s, place t, place a, because I can do it, and I just that's how I work, right? So like literally went through and made like I don't have all the alphabet. Anyway, so here's how it came out. We'll have a demo in a little bit, but very simple. All the stuff you need to set the parameters. You click the button, you come down here, you flip through Cal, and then my support section, I'm just going to reference a website. Right? You don't need any more than that. So under the hood, what am I doing? I just make a globally declared structure that, like when I'm in the UI, it says I have like a position that tells me which one I'm on. Select, it's like if I'm selected, where in that submenu am I? I store the frequency like this, so I made the little integer holder for that. All this stuff. Really simple. I've never done this before. It ends up working pretty well. I did a user study, got some feedback, iterated there. Here's the actual code. It's like, so I'm like, if I'm in UX state position 0, then highlight start frequency. So this function will highlight that, unhighlight whatever it was before, or whatever. So this is just bookkeeping, but it works. So if you guys want, I'll open source the OS. You use it on your products. But I'm not using Linux or Android or any of that. I don't want to install their libraries. Got to do another dev board. So I found another display that had twice as many pixels, and I really wanted that one. I wanted to change to a linear regulator to keep my voltage extremely stable. Actually think about how this thing's going to be powered by a user, so I used a 5-volt DC jack. What I found is, like in the previous slide, I had said, oh, I'm adding an LNA. And I didn't have a separate sub-circuit to test it. LNA is a low noise amplifier. I'm like, oh, I'll boost up my signal. that was stupid because it's like I'm adding costs. And I don't know exactly why I'm doing it, and then I didn't have like a test for it. So if you're doing anything in RF, anything in general, and you have like a section of your board, make a test circuit for that subsystem. So I actually made a test circuit for my LNA, and I looked at it, and yeah, the spec sheet says it, has gain up to 3 gigahertz, but I didn't read carefully enough, and you have to change the matching on the feedback loop for different frequencies, so it was actually attenuating a lot of my frequencies. So one of the things I learned, make an independent test circuit for every single part of your board, and you'll find like you probably have like 8 corners on your board where you have free space, so you might as well do it anyway. So yeah, so this board I'm trying to basically get a new display up, so I have this switch network to attenuate. So when you have this VCO, it's putting out a frequency, it's also got a little bit of energy at the harmonics. That mixes with the signal when they're doing the magnitude detection and screws you up. So I want to have like a switch filter bank. And so I made a test circuit for that because I hadn't done it before.
That's still clear?
This one's 4. So at this point I've gone to 4. Again, this word tenacity keeps coming up. So when I went to this new display, I really wanted to display twice as many pixels, but it just wouldn't work. I couldn't find anything online. I emailed the vendor, they were no help, and I just didn't want to give up. So the way I actually solved this, I ordered a dev board from the vendor, and I put it on an oscilloscope, and I literally just sat there and wrote down every single bit that was being sent over. Like literally, this is the raw data, hard-hitting footage right there. And this is how I was able to get the other display up. So yeah, tenacity. Oh, here's a Smith chart, by the way, if you guys know Smith charts. That thing's cool. So then I had to write a circle function. And PCB layout rules from the expert who's done 4 boards now. For RF, get the vendor to tell you exactly the thickness of the trace that gives you 50 ohms for your reference stack up. Everything in RF you need a lot of ground on your board. Keep very good stitching around all the RF sections, and do everything you can to keep the RF section ludicrously short. For my stuff, that's extremely important because any place where I might have a reflection is going to screw up my measurement. So every time I would find ways to delete microns here and there that would make the overall measurement better. For your high-speed signals, you want fat traces. You want grounds near all the traces. You want ground layers as close as possible to your traces. So again, this V equals LD IDT, less inductance, less voltage ripple. Big deal. For power, you need 1 full layer of ground, cannot compromise on that. So no 2-layer boards. Again, if you're blinking an LED or you're trying to do that, you might be able to get away with making whatever, but if you're trying to do something with super low noise or super high-speed signal, you got to follow the rules. You want your capacitors very near the chips, put extra capacitance in there. You pay extra for this. So like now when I interview electrical engineers, I'll say like, why do you put the power plane and the ground plane right next to each other? See if they've thought about it. And that's because it lowers the inductance, increases the capacitance. No. You see how much time I put in these slides? Know how much capacitance you do. Should be K-N-O-W. That determines your voltage drop. So I equals C dV/dt. So if you know you have 500 milliamps coming out, and you need, want to be able to keep the voltage stable for 10 milliseconds, then how much capacitance you have determines how much your voltage is allowed to drop. So that's another good interview question. Proto 2 is my first form factor build. Again, 4 layers. And again, like to exit the proto stage, you need a very workable prototype or you're not out of proto. The big thing is I added this integrated calibration unit. And as part of my user study feedback, I'm going to 6 buttons. Mechanicals. I've never done mechanicals before. Have you guys done this? First thing we need is a CAD program. So professional guys, NI, SolidWorks, you've heard of them all. What I actually like, FreeCAD. So Mac, Linux, Windows, whatever, it's available. Everything I'm going to do in this whole thing, I only know 2 operations. I know how to make rectangles, and I know how to make cylinders. That's it. So for instance, if you want to make, like when I model this button, I have a cylinder, fat cylinder, and then a subtraction cube. And then I can basically make this to whatever fidelity I want. So it's actually pretty simple. When you're designing, like when you're thinking about how this comes together, I talked to some mechanical engineers. You choose the screw first. You don't design your bosses and then go find a screw. So there's actually pretty buttoned up rules on how this all works. So I want to use plastic because I don't want to pay too much if I make a bunch of these. I find this screw, and for every screw, it has like a thread pitch and a diameter, and there's screw boss recommendations from the vendor that tells you, okay, here's how fat these things should be. Basically, you want 5 threads of engagement is what they call you for a good screw. So that determines how deep it is, and basically you start with the screw and then you just design around it. And when you're also making this thing, you think about how's this going to come together. Assume you're going to make 100 of them, right? Like, if you don't want to put together a bunch of them, whoever you hire or whoever else is going to do it isn't going to want to do it. It's just going to be hard. So I make this super simple. I screw in this board, I screw in the display here, I connect them together and screws in from the back. And so this also isn't too hard. It's just a matter of doing it. Okay, is this all vaporware? Did I actually do something? Let's look at the data. Okay, so measure a few antennas. Again, like a $40,000 VNA and mine. Again, so I do have ripple. I know where that's coming from. I could have smoothed out the data for you, make a nice little simple averaging filter. I don't want to do that. So you can see here I'm measuring just made up this antenna. It's basically resonates at 2.4 gig. You can see it's capturing the essence of what's going on there. The reason I have the ripple is I actually don't have my voltage stable enough on all the power supplies, so I actually have to spin another board. Here's another one that resonates around 900 megahertz. 2010 smartphone. You can see it captures it. 3 dB attenuator, so it's 6 dB loss because forward and reflected. 50 ohm load should be completely blocked. Demo. Okay, so can I have a volunteer? What's your name? Colin. All right. So I just need somebody to hold it. Okay. So, sorry it's kind of small. But so again, very well designed OS, so I can, oh damn it, I'm calibrating it. Okay, so what I'm doing right now is calibrating. So this is automatically doing it. It's just as good as $14,000 version, if not better. So I'm sweeping through all the frequencies, see the progress bar, designed that myself. So again, here's the start, so back out and go. Okay, so what we're actually measuring now, there's some debug information, is just the last state of the cal unit. So what we're going to do is measure a phone, just so you can see. Let me back up as far as possible. Doing a good job. My sweep time is slow. That's because when I was writing, this should be boom, 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 boom. That's something I'm going to improve. It was partly because I was writing the drivers really fast and skipping some of the stuff. Okay, so what we have here is we're looking at the cellular frequency bands. So here is a low band. You can see like a very deep resonance. Here's your higher frequency bands. And so you can use this guy to kind of see the impact of such, well, if you wanted to do the impedance matching or whatever, you would hook it up like this. So for instance, like I can also measure like the impact of the hand effect. So here we have a deep resonance. It's going to, this is S11. It's equivalent to SWR, but it's a measure of, yeah, it's the same measurement. Where are we?
So is that an empty cell phone or just an antenna?
No, this is a full phone.
What's it connected?
So I wired out the primary cellular antenna in here.
So it's connected just to the antenna?
Yes. So anyway, you can kind of, sorry, this is not very well thought out demo. I can't even Okay, so here it's like showing there's some impact to the hand. There's a deep resonance over here that, well, whatever. I don't know what's happening. There's a little bit of, work I gotta get into, but you can see like I can measure stuff. I need to improve the speed, and I gotta get the ripple out. But in general, it does what I want it to do. So, cool. Thank you. Real quick, that's good. Expenses, just so you know, like this, the costs kind of add up. Again, my IDE was nothing, my CAD program was nothing, the PCB license was that, but it kind of crescendos. So I didn't even realize how much it was until it kind of added all up, but that's something to think about. And I'm still not done, which is all the more reason to like get a Kickstarter going or something if I want to make a bunch. Feedback, I'd love to hear it. If you're interested in getting in contact with me, you can find me here on my website or whatever. Yeah. One more thing, get money, get paid. You already knew that. All right. All right, thank you.
Questions?
Yeah.
If you were to do a Kickstarter, what would your target fundraising goal be?
Yeah, so basically if you make about 100 units, your price kind of drops. So to do mechanicals, I think it's going to cost on the order of $12,000 for the tooling. So I asked for a quote from the SMT house. That's on the order of $15,000. So right there, it's 27. Some of my ideas I'd actually like to patent, but so I'd probably set it around 40,000, just because the costs really crescendo. So, and I kind of like the idea of doing a Kickstarter because if nobody wants it, then I can kind of get on to my next thing and take that feedback. The good thing is, a lot of the VNAs, I've spent $3,000, but some of the VNAs cost $15,000, $20,000. So I've already saved money just by doing this. So not only had I a good time learning it, I was able to like make something that I can use on my own to do stuff with antennas. Yeah. Yeah. I could do that. So S12 I didn't have in here, but because it's only like one more component, it was stupid of me not to put it in there, so it's going in there. Yeah. There's going to be a Smith chart. Yeah, you'll be able to put markers, and it'll say, yeah. Do you want to be able to have the embedded matching in there? Like you want to? Okay, cool. So embedded match, I'd have to write all that code, which is doable. But yeah, it'll definitely tell you the impedance, and I'll have port extensions, so you can, cal out your cable. So. So 2 talks ago, there was a guy who recommended Parts Badger as a prototype house, so I used them. Basically, you make I use that FreeCAD tool, and you just output a STP file, step file, and send it over to them. It costs $450, which sucks. So yeah, it's pretty pricey, and then you need to iterate. Everything you gotta plan to iterate on, so it takes time. I got one, and it was ugly. I had to spray paint it. Like it's not, yeah. Cool.
I love that you really concentrate on the stuff that matters, which is having a version of DNA at the end of like 12 months and stuff. Like when you're
It's been like 8.
8?
Yeah.
So when you're making the one-off board for your prototype, where you're just testing something out,
Yeah.
it doesn't bother you at all if your head is not on the grid, your lungs aren't in the road, which stuff really doesn't matter, but
Right.
that's like a lot of people really obsess over that and it delays them by a long time.
Right.
Like when you're starting on stuff like that, like it's obviously a trade-off.
Right. Inattention to detail is one of my strong. So I would probably do at least one more spin on a, so like this one, I'm not sure if they screwed it up or probably I screwed it up, but like I had to sand it down a little bit to get it in there, so it wasn't perfect when it came out. Mostly good. Like all my screw bosses worked and the thing came together as you saw, but yeah, it wasn't perfect. And then to make like a mold where it's easy to make you know, a ton of these, like you need like a tool for that, and that's what's kind of expensive. This one, they start with a block and they just CNC out exactly what you want. But it's like a one-off thing. You don't do that for, you know, more than a few units.
Did you look around for just stand? I mean, it's a rectangular box. Look around to see if anyone is.
No, you cannot let the mechanical engineers win either.